a special instrument we have to use the Fourier transform, which is called the Michelson Interferometer. All right, so I'm going to describe this very briefly here because in your Spec 3 assignment, we're going to dive into Fourier transforms and interferometry in full, glorious detail. So only a brief background for now, okay? So the way this starts, here we have our sample, and here we have our detector. And here we have our source lamp. And that source lamp is an IR source of radiation. And so typically it's just a hot piece of metal. It's that simple to make an IR source of radiation. It's literally just a piece of metal and a bunch of electricity is pumped through it resistively to get that piece of metal hot so that it's glowing infrared wavelengths. That's it, okay? So it's just a glowing metal rod. And so there is a little bit of orange and yellow that comes off of it as well, but predominantly infrared. So it goes through a convoluted beam path, okay? So you can see a set of mirrors will focus it on what's called a chopper mirror, or often what's called a beam splitter. Two synonymous. They're not, a chopper mirror and beam splitter are slightly different, but they give us the same function, and that is they will split the light based on its angle where it's interacting with the mirror, okay? So for example, in this mirror, it allows the light to pass straight through, okay? Light is also reflected at this angle as well, hits this fixed mirror, bounces back and transmits through all the way through the sample, okay? And similarly, when this light that transmits through the beam splitter hits this vibrated mirror, or sometimes we just call it the moving mirror, it will also come back and hit this angle and come down through the sample, right? So like I said, it's a convoluted beam path where there are lots of opportunities for destructive interference and constructive interference. And that is precisely how the technique works, okay? So this is an interferogram. So this graph right here, interferogram. And this X scale right here is the distance that this mirror moves, all right? So there is some center point right here given by what's called zero retardation is often the word we use to describe how this mirror moves. Because it's vibrated, so the mirror is vibrating back and forth, okay? So we often call that modulation or retardation, the way that the mirror moves back and forth. So at the 0 point, and I know it doesn't look like it on this figure, but at the 0 point right here, the F distance equals the M distance. And so that will give us maximum constructive interference, okay? And as this mirror moves, you can see there's huge sweeping destructive interference where it goes all the way down, and then constructive interference where it comes back up, and then destructive interference, and so on and so forth. And you also notice that it's symmetrical about the other side of the mirror, right? The mirror is moving back and forth this way about this center point, okay? So it will be a two-sided interferogram. And so what this ends up doing, because our IR source is broad, so it has a whole plethora of different wavelengths, those are all interfered with constructively and destructively in different ways as this mirror is vibrating back and forth. And so what this does is it creates insanely high spectral resolution. Because as you can see each of these data points right there, right? Each one of those data points will give us a unique combination of wavelengths that make it through and onto the sample. And so by the time you've scanned through all of your wavelengths, and that's achieved by literally just moving this mirror back and forth, you will have passed through every single wavelength available from this lamp at insanely high spectral resolution. The Fourier transform is then the mathematical algorithm that converts this signal right here into a spectrum. That's right. And so we have to view this on a time domain. Even though it's showing this as a distance, this moving mirror has a certain velocity that we program in the spectrometer. And that velocity multiplied, the distance that the mirror moves divided by its velocity will give the time domain of this. The Fourier transform converts that into an actual spectrum. And when I was an undergrad, I used to think that process was just like magic. How you go from this figure into an IR spectrum, it's kind of amazing. It's what we're going to be doing in our Math 3 assignment. So that should be very cool. Okay, so I've been talking quite a bit. So I'm going to break this up into another lecture. So I'll pick up with this in the next one. Alrighty, folks.